Okay, so I am Sridhar Iyer, and I am perhaps the longest staying faculty here in this room right now. I've been around for 24 years as a faculty in IITB. So I was in computer science for more than 15 years, and then I moved to education technology. So I've done large classes, I've done project-based classes, I've done small classes, many of those things. And so I'm kind of trying to share some of the experiences here. Okay. All right. So let's start with some little bit of getting the blood flowing, right? So consider programming as taught in many schools today. A teacher typically explains the syntax and the logic and then asks students to go through some solved examples, gives them some homework exercises from the book, and then in the exam they are asked to write a program for one of the textbook problems, right? Are these students likely to score well in the exam? How many people think yes? Okay. How many people think no? Okay, there are a few people who think no. How many people are not yet thinking? Alright, okay. So we do have to think about it. So again, it depends upon the type of school actually. So it's not a very clear yes or no answer even for such a question. I, for example, would vote yes, because these students will mug up the answers. Okay, so if you are going to ask a rote question in the exam, something which they are already familiar with, they would have gone through it, they would have done that. So 80% of the students getting 80% of the marks is kind of the benchmark for having done well. Okay, but if you ask a slightly different question, okay, the same students are now given a problem that's unfamiliar to them, but it's still at the same level as the textbook problems. Okay. Now they have to write a program, run it for a few test cases and give the output. Okay. So are these students likely to be successful now? Yes? How many yeses? Okay, so we are down to 0 yeses. From some yeses, because some of us are familiar with the whole idea of rote learning and we know that okay, students do tend to sometimes mug up the program itself. Like I've had students rattle off a C program. You know, I mean, it just rattled me. How can you? And this is a 10th standard student, okay? So it's amazing how they are able to just reproduce the entire syntax. So, but in this case, we know that look, 80% of the programs are, so actually we've moved quite a bit from this in the sense that, yeah, so thank you for your answers. So in the sense that we do give assignments, but then even the assignments are not achieving the entire target, right? I mean, students are not doing all the assignments diligently, some copying is happening, something is happening. Eventually there is this discontent that we have as instructors that look, learning is not happening in my class as well as I would like it to happen. That's the discontent we are talking about. Okay. So now how do we fix that? Okay. So there are 3 basically questions that we have to ask. Okay. So one is we have to be very clear as to what we want them to learn. Okay. So I'll come to exactly what that means in a moment. So the first question is what should they be learning? Can we define it as precisely as we can? Okay. The second point is, okay, now what can we do to help them to learn it? Okay, as instructors, so those are the instruction strategies. And at the end, we want to assess how are they learning it? Okay, how well are they learning it? So that's the assessment. So this is called your triangle of learning, effective learning. Okay, so the triangle of effective learning basically connects these 3 components of our instruction. Okay. So one is the learning outcome. We'll get into details of each of these in a moment. Okay. One is what we want them to learn. Second is are they learning it? And third is my strategy of teaching them suitable for them to learn it? So these are the 3 things that we are trying to connect up. Okay. So let's do a quick activity. Okay. So think of the course that you're going to be teaching this semester starting next week. Okay. And write one learning outcome. So everybody has a pad, right? Pick your course and write one learning outcome. Okay, I mean, it's not a very, I mean, I don't want your entire course syllabus Okay, just one learning outcome. All right. So, okay. So, how many of you have the word understand in your sentence? All right. So now, so I also used to do the same thing. Okay. So this used to be my thing. So I am teaching a basic course on computer networks, and my learning outcome is understand networking protocols. I want students to understand networking protocols. Okay. So the question here is, what does this understand mean? Okay. Do I want them to rattle off names of 5 protocols? Do I want them to be able to describe how one particular protocol works? Do I want them to be able to actually implement the core of a protocol? Do I want them to be able to troubleshoot a protocol as it is running in the network? Okay, all of these qualify under the term understand, right? So that is the thing that now we have to refine. Okay, so like if you remember, we went back and we said, can we define it precisely, right? So this precision is what is important. So instead of simply saying I want them to understand, now what happens when we say understand? We have one idea in mind. Okay, so I have an idea in mind that when I say they should understand protocols, it means that they should be able to go to a network simulator and they should be able to set up the network and they should be able to make the packets go and so on and so forth. And I do have activities in my class which makes them do that. But what they feel by understand is that, yeah, I should get that diagram which he drew on the board and I should be able to say that, okay, if a packet comes from here, that's the way the packet is going to flow. Okay, they are not wrong, right? That's what they have got from the whole word understand. Okay, so if we want to make more sense of this, there is a framework which helps us to do that. Okay, so this framework is called Bloom's Taxonomy. It's fairly old. I mean, it's been revised and different people have come up with it and all. But the basic thing to keep in mind is that there are several levels. These are called cognitive levels. Okay, and the more clear we are as instructors as to what level we want the student to understand. So the understand, let the understand word be there. But now you try to define what is the level of this understand. Is the understand at the recall level? Do you mean that you want them to be able to recall facts when you say understand? Okay. Or do you want them to be able to explain or interpret something when you say understand? So each of those has its own corresponding level. Okay. So this itself is an entire hour, and there is another video on this. This is Sahana's video from some earlier year. So of talking about the learning objectives, and she takes you through an entire exercise of writing objectives and so on. So since we don't have so much time, I'm not going to go into all these levels, but I'll just talk the key thing to remember here. Okay, so the key thing to remember is this column of action verbs. Okay, so instead of using the word understand, try to use some verb, some action verb, which will say what you expect the student to be able to do. Okay, so it's sort of like to be able to demonstrate. I need the student to be able to take 2 pieces of code and be able to say, okay, what is the difference between them? Okay, so student should be able to do dash. So whenever we use any of these, right? So if you are doing, let's say you are asking them to design something, then you will say, okay, student should be able to design something. So you automatically know that your understand is met only if the student is able to perform at that level. Okay, so there is no rote learning possible when your expectation is set at that level. Okay, so that's the basic idea here. So these lower 3 levels are called the lower levels of Bloom's taxonomy, and these are called the higher levels, and generally actually apply upwards. So the same understand question that you had written, can you write an assessment question for that?
I have written something like interpret and describe what happens given a situation, or let's say a physical problem, it involves solution and things.
Okay, like interpret and describe.
Yeah.
Okay.
So this is for a machine learning data analytics course. So give a problem and then ask what's dependent variable, what's the independent variable, and which tool is applicable, and use the tool to solve the problem.
Okay, so determine the dependent and independent variables and use an appropriate tool for solving the problem. Okay, would you like to go? Yeah.
The question is, outline or detail how do you go about establishing a particular mechanism of a reaction which is being proposed below. So you give tools to establish this mechanism.
Okay, detail the mechanism of a reaction that happens, right? Okay. Okay, see, this assessment question that you all wrote is much clearer than the learning outcome that you wrote, right? So that is the key. They are both tied together. Okay, so because in your mind you already have the learning outcome in mind, because you know the assessment question that you want to set. So that also is a very useful way of designing, you know, to look at, is my assessment aligned with the outcomes? Okay, so it's the same taxonomy which works. So one person said determine something, another person said interpret something, third person said do the detailing of something. Okay, so all of these are again verbs which you will find in this different levels of, so you are talking at the apply level, one person is talking at the evaluate level. Okay, so all the questions that we are talking about also fall into the same levels as our learning objectives. Okay, so that way it's kind of getting two things done with one task, right? So just use the framework to both define your learning objectives and your assessment. So these two go hand in hand, because that is the time when you are making check, right? So for this objective, is the objective met? Okay, so there's nothing much more hard to talk about in terms of assessment. So now comes to the third thing. So this is an interesting activity. Okay, so think of one activity that you excel at doing. Okay, really excel. It can be anything. It doesn't have to be your course. And think about why you're so good at this activity. So I'm going to do some magic. I'm going to guess your answer. Okay, so one of your top 3 reasons is likely to be practice or experience or some version of that. How many of you had that? Okay, more or less got it. Okay, so that's the key point to remember as instructors. That is, if that's the only thing you remember from this session, that's fine. Okay, that you became good at something by practicing it. That's the only way your student will also become good at it. All right. So as learners, we develop mastery through practice rather than simply listening to lectures or watching demonstrations or whatever it is that the instructor is doing. So as teachers, we must ensure that we provide students with sufficient and timely opportunities for the same practice to get that level of mastery. Okay, so the keywords here are sufficient and timely. See, because often we think that I have given them problem sets, I have given them a tute sheet which they can solve later. Okay, but that's not timely. Okay, so the timely is to be able to do something while you are teaching. That's the timely part of it. So I'll just come to it in a moment. Okay, so there are some techniques to do that. How to provide this? So one way is called active learning techniques. Okay, where students go beyond listening or taking notes in the class, and they are actually asked to figure things out during the class. It needs a little bit of an attitude shift for us, but I think that's no longer such a problem. I think the newer generation is more in tune with being able to look at how well they are learning. Okay, so here's an example. Okay, so let's say you're teaching this class, some physics class. Okay, an object floats in water but sinks in oil. When it floats in water, it's exactly halfway submerged. If we slowly pour oil on top until the oil completely covers the object. Now what happens to this object? Does it move up? Does it move down? Does it stay in place? I'm sure there's an equation which governs it. I don't know the answer. Okay, so the thing is, now some people think it stay in place. Okay, some people may think that yeah, it should move up, because it's going to float up in sink in oil, right? Okay, yeah, so something's going to happen. Some people may think that it will get submerged a little bit. Okay, whatever it is, every student will have their own logic for why they picked that answer. Okay, that's the key point. So the first thing we have to do as instructors is to make them express that logic. So you have to make them vote it. And the next thing you want to do, make them do, is tell them to discuss with their neighbor. Okay, so we don't have that much time, so I'm not carrying out the entire activity. But you say, okay, talk to the other person, convince the other person that you are right. So there will be a lot of noise in your class, which is a very good thing. Okay, so there will be a lot of talking that will happen in the class. And then you ask them to vote again. Okay, and then you'll be surprised to find that they either converge towards the right answer. Sometimes they also converge in some other direction. But as an instructor, then you know exactly where their thinking is, why they have come to a particular answer. And then you give your lecture about the topic. Okay. So this technique is called peer instruction. So once again, there is a video on it, and to help you, there is a 2-page sheet which can be downloaded from the Education Technology Department's resources. I think we can make it available, right? As a, even as a hard copy we can make it available, which you can simply use for your own course to create these kind of questions. Okay, so it's basically take an MCQ and instead of putting it in the exam, put it in the class. Okay, and make students vote. So that is the idea here. Okay, so you ask a question, make students vote individually, and this voting is very important. You know? So if you straight away tell them to start discussing, they won't commit to an answer. Okay, because I'm not sure what the answer is. Okay, it's very natural, right? Human nature. I'm not sure what the answer is. I don't want to expose my ignorance to another person. So I will kind of keep it vague. So that bridge you have to cross by forcing them to vote. And it can be anonymous. And once you cross that, then they will discuss. Once I have committed to answer 2, right? You said it will stay in place. Once she is committed to it will stay in place, now she has to give an argument for why she thinks it stays in place. And if I have committed to saying that it will go up, I have to argue. So that's where the entire learning happens in the peer discussion step. And then they vote again, and then this is what you do as the class discussion debrief, and then you can go to the next question. Okay. So for want of time, I'll just show you another example. Okay, what is this happening one by one? Okay, so let's say you take coding. Okay, you show this very standard example, right, of pointers and what are we doing with them. So again, this is a good question for a peer instruction, where you can ask them to identify which of these values will be there in those variables. So some students will work it out correctly, some students will not work it out correctly. You will get an idea of where the confusion is happening between an address and a pointer and so on. All those things will become clear, and then once they do the discussion phase, once again they will converge towards an answer. So the understanding of the class goes up and your effort actually goes down. Okay, so this I have done in a class of 450 students, CS 101. Okay, you don't have to do anything, they teach each other. Okay, so because it's just peer instruction. All right. So, okay, here is an example with visualizations. Let me see if I can play this. Okay, it's an interesting one. Okay, so there's a video. It's a 7-second video. Okay, so this person is going to push this balloon. Okay, so what will happen to the balloon when they start pushing it? Okay, so the balloon is like a helium balloon. It's attached by a string or at the base here. It's enclosed in a glass box. You can add a whole lot of explanation around it. But the basic question is, when I start pushing it, what's going to happen to the balloon? Is it going to go ahead? Is it going to go behind? Is it going to stay in place? How many of you were quick enough to observe what happened? Okay, some of you did great. Okay. Yeah, okay. So basically the thing is that in this case, if you see, you find that it goes ahead and then it comes back and it does all of these things. Okay, so normally when we explain a topic like this, our instinct is to show the video. Okay, our instinct is to say, hey, look, see what's happening to the balloon, it's going ahead, see, it came back, right? We tend to get excited by the phenomenon and we want to draw their attention to the phenomenon. Okay, that's a good thing. But then what happens is we don't realize that they are not engaging so much with the idea. So on the other hand, if we say that, okay, look, I'm going to play this video now, and you have to predict what's going to happen to the balloon. Okay, so you automatically engage their thinking. They are trying to apply some principle. Somebody will say inertia, somebody will say something else, and they'll try to predict something. And once the prediction is done, then when you say, okay, why don't I play it, and you check what is happening, and then they'll be wondering, okay, I predicted that it's going to go back, but the balloon actually went front. Why did that happen? All those questions you will start getting, and you will have a very engaging class. Okay, so the key idea here is very simple. Don't show the entire answer. Okay, don't show the entire demo. Okay, so play the visualization up to a certain point. I mean, this will work for any visualization, whether it's a video or whether it's a simulation or whether it's a program, anything it can be. As long as there is some observable output that is there, you can use this technique. You can play it up to that point and pause at a critical point and ask them to predict. Again, you can ask them to discuss with each other. If somebody says this versus, like for example, somebody may say yes, it's going to move to the left, or somebody else may say it's going to move to the right. You can have them argue with each other as to why it's doing right or left, and then you can show the rest of the result where you talk about the why whatever happened. Is that making sense? So this is the broad idea of peer instruction. No? Use small questions, have multiple answers, force the student to pick a choice, and then argue about their choice. That's the essence of peer instruction. Okay, so it can be implemented in lots of ways, right down to Mentimeter, or even simple show of hands, how many people vote for this and so on. So I'm not going to go into the details of that. There's about 5 minutes left. So I'll just do one more idea very quickly. So let's do one more thing, one more idea. Okay, so imagine a 90-minute class in a large auditorium with fixed seats. Okay, this is our LHC. Okay, or this room. This room is still not that, yeah, it's fixed seats, but it's not that large, right? So now predict the percentage of students who may be showing engaged behavior with the content at various instants of time. Okay, not your lecture. Your colleague's lecture. Okay, your lecture will be very engaging, I'm sure. Okay, so what will be the how will the graph look? You can just wave your hand and show me. Engagement versus time. Okay. Somebody else? Yeah. Your perspective. Okay. All right, something like that. Okay, so somebody else drew a drop tail straight away. Somebody else is saying, okay, for some time they'll be engaged. It will go up and then come down. Okay. What else? Sorry?
Depends on the class time.
Depends upon the class time. Yeah, at various instants of time, right? From the beginning of... when the class happens. Yeah. If it's 11:30 class or whether it's a 8:30 class. Yeah, that also is true. Yeah, in some places it may be right at the bottom, right? If it's a 8:30 class or something like that. All of that is possible, right? So now, let's ask this question, okay? Come up with one technique that can be used to convert your graph into something like this, okay? Where this is the 80% engagement level. So 80% of the students are engaged for 80% of the time. In a class of, let's say 100, 200, whatever is the class that you're going to teach. Okay. One technique. Maybe talk to each other, just since she gave us 5 more minutes. Okay. Any answers? Any suggestions? Yeah, go ahead. Mike, pass the mic, please. Yeah.
Peer instruction again.
Peer instruction, very good. Okay. Yeah, do peer instruction. What else?
Tell stories.
Tell stories. Okay. Tell stories. What else? Yeah, give some activity in the class. Okay. Okay. Anything else? Any other? Tell a joke. Nobody said tell a joke. Often I get that answer. Tell a joke. Okay. So yeah, so the tell stories. So let's look at all these answers. Okay. So the tell stories, while from the instructor's perspective it sounds like an interesting idea, we don't know if that person is listening to your story. Okay. That's what happens. Right now, who's the most excited person in this class? I am the most excited person, right? It's always true. When you are standing here, you will be the most excited person. You will be jumping around saying, wow, what an idea, how well I am teaching, all that will be happening. Okay, that person is just waiting to say, okay, when is this chai going to come? Okay, so that is the problem, right? So anytime we are doing the work, we can't be sure of the engagement. Anytime they are doing the work, you can be sure of the engagement. Okay, so now when you were talking, you were engaged. Okay, so this is also a technique. So this technique is for slightly more complex problems. Okay, so this technique is called think, pair, share. So first you think, so where you thought and you said, okay, the graph will look like this. And then as a pair you did some activity saying that, okay, talk to the other person, designed a new solution, how to fix the problem, etc. And then as a class we shared the solution with everyone. Okay, so this again is some very good noise that will happen in your class. When you do that, you'll find that, okay, initially people will say, what is going on this, what is this pair and all. Nobody will talk. Just let that uncomfortable silence be for a few minutes. Okay, then students will start talking. At some point the noise will plateau out. When the noise plateaus out, you know that, okay, most people have finished discussing. Even it doesn't matter how large the class is, whatever be the size of the class, the noise will increase, plateau out, come down. Once it starts coming down, you say, okay, most people have finished discussing, you bring them back to the class, you talk about the idea. Okay, so I'll just quickly show you two examples of using this in a technical topic and then we'll close. So in the think phase, the teacher poses a specific question about the topic. Okay, for example, how will you sort a given set of numbers? So I am teaching sorting algorithms in CS 101. Okay, so this is a question I pose. How will you sort a given set of numbers? Whichever way you want to sort. Okay, so everybody knows how to sort. They may not know the name of the algorithm, but they know how to sort a given set of numbers. So the think phase has to be easy so that everybody can take a crack at the problem. Then in the pair phase, you tell them to pair with each other and do some task with it. Okay, discuss the pros and cons of each other's sorting algorithm. Okay, so somebody may say that, okay, I am going to pick one by one and put them in order. Somebody else is going to say that I am going to do some merge sort, whatever it is. Okay, so let them talk about what is the pros and cons of their solution. And in the share phase, the students share their thinking with the entire class and you facilitate discussion on the topic. So you discuss different types of sorting algorithms. So when I did this in CS 101, so typically sorting algorithms goes for like 1.5 hour classes. Okay, so we finished the whole thing in one class of 1.5 hours because all the ideas came out from the students. All I had to do was to say, write the broad idea and then give it a label. I had to say, okay, this is called merge sort. This is called insertion sort. This is called selection sort. That was it. All the ideas came from the students. Okay, so that while it may appear that, okay, it will take a lot of time away from your lecture and away from your content, it actually saves a lot of time because they are also engaged and they are thinking at a deeper level. Okay, here's another example. So for a design problem, if you want to design a taxi scheduling service, again the idea is in the think phase, you give a very simple question which everybody can attempt. In the pair phase, you make them build on it. And in the share phase, we discuss everybody's answers. Okay, is that making sense? So again, we have a constructor, which is a 2-page constructor, which will take you through this for your subject, which you can simply use to create interesting think, pair, share questions. I think we have a repository also, right? Yeah. Okay. So, no, repository of collected TPS questions, I think or maybe we'll start one. Yeah. Okay. So the PPCCLT channel on YouTube has all these lectures recorded from some previous time. Okay. Active learning, peer instruction, think, pair, share. Okay. So this is the last slide. So these are long videos. So what we will try to do is maybe, if we get enough TAs, we'll try to identify in which portion is the example and then we'll send you a short clip. Nowadays it's that shorts, right? Nobody wants to see the long ones. So that's what we'll try to do. Okay. So this is basically it. So you define your learning outcomes, be clear about what you want the student to achieve and make them grapple with the content in the class, make them do something in the class to get there. That's it. Thank you.